Welcome to Lecture 15 in Chemistry 51C here at UC Irvine. It's the quarter of campus shutdown and remote instruction caused by the coronavirus. Today, I wanted to talk about aphid honeydew. It might seem like a rather random topic, but these small green bugs on this plant are aphids. They stick these little probosces or something into the plant and then suck the phloem out of the plant. And quite often they're tended to by ants that basically domesticate and take care of the aphids and then get them to squirt out some of that sugar-rich, what's called honeydew, which is good for the ants. The ants protect them and make sure they're taken care of. Why am I even talking about this? Yesterday, I was with my daughter over at the San Joaquin Marsh Preserve. Really an amazing place to walk around and see bird life, plant life. And we saw in these milkweed plants, I stopped to take Jules' picture and she saw these ladybugs, and we got interested in the ladybugs, but it was clear that the ladybugs were munching on aphids on the underside of these milkweed leaves. I think it's milkweed, not a botanist. And so it's cool. And when we looked a little further, we could see ants all over the plants on the ground, moving around. They didn't seem to be actively doing anything with the aphids, but kind of brings back these memories of nature shows where you see ants tending to aphids and getting honeydew out of them. And I got interested in what is this honeydew, or what is this liquid that aphids are getting out of plants? And if the ants are getting any honeydew out of the aphids, then what's in there that they in that honeydew? Why don't the ants just eat the aphids? When I looked online, if you want to find out information about chemical composition, that's usually what you have to write the word composition when you do an internet search. So I typed in aphid, milkweed, honeydew, composition, that's the keyword. And I found a bunch of research papers where they tabulate and quantify the chemical components in honeydew. And a lot of it was not very interesting. Sugars, kind of the obvious thing that the ants want. But what was interesting to me is it seemed like one of the main focal points of this paper was to quantify the amount of a class of compounds called cardiac glycosides. These are derivatives, basically derivatives of steroids, but these are well known because they have activity against the human heart. These are used as medicines, cardiac glycosides, that's what the name implies. And two of the critical ones that they were studying in that research paper was digitoxin. I'm not sure they could distinguish these using on their liquid chromatogram against the internal standard they had of digitoxin. But digitoxin has an H where the X is, digoxin has the OH. And the digoxin is the more common one that's used clinically. So some people with some heart ailments will take these are very potent compounds, these very tiny doses of digoxin, which come from plants, usually the foxglove plant. And these are used to modulate heart activity. They target the sodium-potassium ATPase, which is an ion pump that's essential for heart function. And so these compounds modulate heart function. Why are the aphids, the aphids seem to be sucking phloem out of plants and collecting a lot of sugars, but these are also present in milkweeds, mainly things like oleander. It's a common constituent. But apparently these compounds don't kill, these could be proved lethal to humans at higher, or mammals at higher doses, but clearly they're not affecting the aphids. They're not affecting any ants who are consuming these things. It's clear that eating aphids doesn't kill ladybugs. They love them. So this is just a really interesting class of compounds. If you end up going to medical school or dental school or whatever, you'll take a pharmacology course and they'll ask you to learn about cardiac glycosides and their biological function. So very cool class of compounds, kind of part sugar, part steroids, and that's cool. 3, 2, 1. When we left off on Friday, we were talking about the synthesis of amides from carboxylic acids under a very special set of conditions that are particular to the industrial synthesis of nylon, and these are not in any way general conditions. If you take a carboxylic acid and you mix it with an amine, the first thing that's going to happen is an acid-base reaction. The lone pairs on nitrogen are going to deprotonate the carboxylic acid until you'll end up with a species that's not electrophilic. The lone pairs on this carboxylate are donating into the carbonyl. And so the carboxylate anion already has a nucleophile that's internal donating into the carbonyl group. So this is not really electrophilic. Moreover, when you protonate the lone pair on the nitrogen, there's no lone pair left. So that's not nucleophilic. And so that's why this is not a good way to get amines to attack carbonyl groups. And in practice, you have to thermalize these at hundreds of degrees in order to get these to work. And if your R prime or your R group have any functionality to them other than just CH2 groups, these reactions simply don't work. They would give you junk. I already told you what conditions to use if you want to take a carboxylic acid and an amine and condense them together to form an amide bond. Use the reagent DCC, dicyclohexyl carbodiamide. It's simple to write out DCC. It's just as simple as it is for you to write out some special thermolysis conditions or a delta symbol. And so this is the way I want you to form an amide bond if you want to take a carboxylic acid and amine and directly condense them together. So we've talked about the synthesis of esters. We've talked about the synthesis of amides. Let's go ahead and talk about the hydrolysis. The hydrolysis to go back to carboxylic acids. And I'm going to give you two recipes for hydrolysis of carboxylic acids. One recipe is going to be the reverse of the Fischer esterification reaction. In a Fischer esterification reaction, we take an alcohol and a carboxylic acid, and we mix them together in the presence of a strong acid, like hydrochloric acid or sulfuric acid. And we rely on the fact that the methanol is the solvent and is present in excess to drive the equilibrium towards ester. If we want to go back to the carboxylic acid, all we have to do is replace the methanol solvent with water, and then it goes back to the carboxylic acid. It's the same mechanism, the same reactive intermediates. Let's go ahead and draw the mechanism. It's the reverse of Fischer esterification. So you start off with your ester derivative, your ester, and we'll go ahead and symbolize our acid catalyst with the letter HA. And there's a lone pair in the carbonyl that's going to protonate, be protonated by the carboxylic acid. It's not easy to get a proton on that carbonyl group. That's why we need a strong acid under these reaction conditions. And 10 times more acid means 10 times faster, because we'll have 10 times more of this protonated species present. I'm not going to draw equilibrium arrows for each of these elementary reaction steps. They're all in equilibrium with each other. I just want to show the steps going forward so that we can explain how we get the carboxylic acid out as the product at the end of this transformation. So we protonate the carbonyl. Let me get that proton on there. That's fantastic to see. Now it's easy to attack that carbonyl group. Even water, a lame nucleophile, can attack that carbonyl group. So let's go ahead and depict the attack of the water. It's so satisfying to push these electrons up to that O+, and that positive charge, the formal positive charge on the oxygen, will disappear. And we'll end up with this tetrahedral intermediate now. And that water nucleophile that just added in is now sitting there as this oxonium ion. And here's our methoxy leaving group. Now we can't push out this methoxy leaving group yet. We're going to have to pull a proton off this oxonium O+ and put it on the methoxy group. That's a two-step process. Now the first step, we generated A- as a counterion. I'll draw it there, but it's still hanging out. And for these intermediates, I'll draw it down below, just kind of seductively poised near this oxonium, and I'll now make that deprotonate. And so now we're ready to pull the proton off of the H2O+ and put it on the methoxy group. So after this step, we're going to have this HA sitting around. And now this bottom hydroxy that used to be our water is indistinguishable from the carbonyl oxygen that got protonated. And we have our acid catalyst sitting around. I'll draw it down below here, right next to that methoxy group lone pair. And now we'll show the methoxy group being protonated and turned into a good leaving group. It's equally probable to protonate all three oxygens here. That's all happening in solution. But we're just trying to show the steps that lead to formation of the carboxylic acid by turning this methoxy group into a good leaving group. Now that methoxy group is a good leaving group. Now it can leave as methanol, as a neutral molecule. I can use the lone pairs on either one of these hydroxy groups to push out that leaving group. It doesn't just leave, it gets pushed out. That's what makes it it's such a great ionization type process to lose this leaving group. Way better than the SN1 reaction you learned back when you were making T-butyl carbocations. So now we generate this species that looks just like an ester that's protonated. That's exactly what it is. And we simply need to remember that when we pulled the proton off of this HA, we still have this A- floating around. And we're going to now draw it up over here, right next to that, that protonated carbonyl. And now we'll pull that proton off. That regenerates our catalytic acid, and it generates the product of the reaction. I've messed up here. This should be an H. Let me put a big X through there. That should be the H. The methanol should have left as a leaving group. That's down there. Yeah, sorry about that. And that explains how you get a carboxylic acid mechanistically under acid-catalyzed conditions. These are the same intermediates that we drew for Fischer esterification. It's the, you just change the arrow pushing in it. So I expect you to know the mechanism for this reaction. It's kind of a freebie. You memorize the mechanism for Fischer esterification, and you've pretty much memorized the mechanism for acid-catalyzed ester hydrolysis. It's certainly, once you've memorized the mechanism for Fischer esterification, this is certainly easy to understand, but it's not the most common way to hydrolyze esters. The most common way to hydrolyze esters is not with acid, it's with base. It's just such a better reaction. As long as your molecule is tolerant to base, to hydroxide anion, this is the preferred way to hydrolyze an ester. And that's to use not just catalytic sodium hydroxide, but to use one equivalent of sodium hydroxide. This is not base-catalyzed because you consume one equivalent of base in the reaction. We call that base-promoted, just to distinguish it. You don't regenerate the base mechanistically during this reaction. The mechanism for the reaction involves sodium hydroxide simply cleaving this bond, and the products that you generate in this process are have to give me a second here to try to get my notes right, going here. So we're using sodium hydroxide and water, and the products of this reaction, we're going to get an alcohol and a carboxylic acid derivative. But we don't get the carboxylic acid because we're in base. You can't have carboxylic acids floating around in base. They get deprotonated. Let me make sure I count out the same number of carbon atoms here on this chain. I don't want to make a mistake on that. Because you're in sodium hydroxide solution, any carboxylic acid that you generate is deprotonated in order to give you this carboxylate anion. In this case, the counterion would be sodium. If you were using potassium hydroxide, it would be the potassium salt. And so these are the products. And this process is the same process that they use to cleave fats and lipids into alcohols and long-chain fatty acids. And those sodium salts of long-chain fatty acids are soaps. That's the soap you use to wash your hands in a bar of soap. So we call this saponification, which stands for soap making. And it's not catalytic in base, it's stoichiometric. Mechanistically, it's easy to understand what's happening here. You start off, and let me point out what makes this so highly used, is these reactions occur at room temperature. That hydrolysis and the Fischer esterification, you have to boil those reactions. You either boil it in methanol or you boil it in water. It's not easy to get a proton on a carbonyl and then to attack it with an oxygen nucleophile. Whereas here, step one for this mechanistically, the mechanism for this reaction involves hydroxide. Don't draw a B because we're not using this as a base, we're using this as a nucleophile. The mechanism starts off with attack on the carbonyl. There we go. And then you generate this tetrahedral intermediate. I'll draw the hydroxy group up here now. And then you push out the leaving group. Boy, it's so much easier than that acid-catalyzed mechanism. There's no proton transfers going on there yet in that system. There's our leaving group. That would be that propanol leaving group. And initially we have a carboxylic acid, but that carboxylic acid isn't going to last for more than an instant because you've got bases floating around, hydroxide anion, you've got this alkoxide anion floating around. Just to make things mechanistically simple, I'm going to draw the arrow pushing for deprotonation coming from the alkoxide anion. There we go. And that's what leads to, it's such a simple three-step mechanism to get to the end here. Mechanistically, it's simpler. These reactions are so much faster than the hydrolysis under acid-catalyzed conditions. Now, because you often want the neutral carboxylic acid, in organic chemistry, we extract products we want. Generally, we extract those into organic solvents and then evaporate off the solvent. So if you want the neutral carboxylic acid in this reaction, we have to show how we generate that carboxylic acid. So if I were to depict this reaction using reagents, I could simply write sodium hydroxide. I don't have to write water. I don't have to write room temperature, because if you don't show the temperature, the reader assumes that it's being carried out at room temperature. But we need to show how we get the proton on the carboxylate anion. We would have to follow this up with an aqueous HCl workup. Aqueous HCl. If you didn't write aqueous and you just read HCl, I would count that correct, but we just want to make it clear that we're not trying to do anything fancy like protonate the double bond or anything. We just want to protonate the carboxylate anion. And again, it's so common to do this. If you write a research publication, you don't show workup conditions like for Grignard reactions, but it's understood by anyone that when you do a saponification and you draw the neutral carboxylic acid, that you're doing an acid workup to neutralize that. But in this class, I want you to show that as a second step. I want you to write aqueous HCl as following a saponification if you're trying to generate a neutral carboxylic acid. Saponification, the hydrolysis of esters, is super facile. If you've ever taken a solution of sodium hydroxide base and rubbed it between your fingers, it feels slippery. It feels like you're rubbing soap between your fingers, and that's because the lipid molecules, which are esters, in your dead skin are being saponified and turned into soap. They're being converted basically into ivory soap or any kind of handbar soap, and so it feels slippery because you're synthesizing soap from the lipids in your dead skin cells. Don't leave it on there for an hour, but that doesn't hurt your fingers just to do that simple experiment. Wow. Base cleavage, base-promoted hydrolysis of esters is so facile. Room temperature, way easier than the high temperature, than the elevated temperature acid-catalyzed hydrolysis. With amides, there's no easy way. There's no mild conditions for hydrolyzing an amide bond chemically. If you had an enzyme that just happened to accept it as a substrate with high affinity binding, you don't have to worry about the harsh conditions. But for a course in organic chemistry like this, we're using chemical reagents, and it just takes either strong base and aggressive heating or strong acid and aggressive heating. And not a little bit, it takes a lot of base or a lot of acid. So let's go ahead and talk about these conditions. If you want to hydrolyze an amide, we either need to use concentrated, not the most possible concentrated, but very concentrated base, sodium hydroxide, water, 100 degrees. You don't have to write the time on here. I simply indicated that just to make it clear. It's like you still have to wait. It's still a slow process, even when you're stacking the deck heavily in your favor. So under basic conditions, when you do this hydrolysis for those of you who aren't comfortable with normality, some acids like sulfuric acid donate 2 protons, and you want to distinguish that, so you use this abbreviation normal. But for a normal base or an acid that only donates 1 proton or accepts 1 proton, normality and molarity are the same. You could write 4 molar if you're not comfortable with normality. Go look that up on the web or in your general chemistry textbook, but you're fine with using, sorry I used normal there. I don't think that helps you here. Okay, the product of this is the carboxylic acid, but you're in strong base. There's no way it's going to be the carboxylic acid. That's going to get deprotonated under the conditions of the reaction. So just like saponification, if you hydrolyze amides under basic conditions, you don't get the carboxylic acid, you get the sodium carboxylate salt. The amine cannot be deprotonated. No simple base short of butyllithium will deprotonate this NH2 group. So forget about that. It's a base itself. Base isn't going to regular bases won't deprotonate that. But you will, one of your components will be charged. When you do the hydrolysis under acidic conditions, there you get the carboxylic acid in its neutral form, right? This is not enough to put, except for a mechanistically small amount, a tiny bit of this at equilibrium, which would have a proton on there. But the hydrochloric acid is strong enough to protonate the amine product of this reaction. And so that ends up being generated as the ammonium chloride salt, because the HCl in your reaction mixture protonates the amine. So no matter what, one of your two products is going to be charged under these conditions. The other one will be neutral and soluble in organic solvents and able to be extracted. So, these are the harsh conditions for hydrolysis of amides. In section 22.14, they talk about cyclic amides, and a cyclic amide is called a lactam. And in particular, that section of the book focuses on a class of 4-membered ring cyclic lactam drugs. Maybe I should put R here, called beta-lactams, like penicillin. You can hydrolyze these just like you hydrolyze any other amide. Just remember, when you hydrolyze cyclic lactams, the two pieces, the carboxylic acid piece, is still going to be connected. So if you use that sodium hydroxide, 4 molar, in water, and 100 degrees, the two products you get, like the sodium carboxylate salt and the amine, are still going to be attached to each other. So, and a lactam is just a cyclic amide. The beta means that the nitrogen is attached to this chain at the second carbon, the beta carbon from the carbonyl. There's a section called Summary of Nucleophilic Acyl Substitution, and there's a table in there that has every possible combination of convert an acid chloride into amide, yes, into an ester, yes, into a carboxylic acid, yes, but you would never want to do that, into an anhydride, yes, but that would be pointless. So every possible functional group interconversion in that section, they try to summarize that for you. And I'm simply going to direct you here to know the table. That's in the book. Those transformations are really what this chapter is about. Section 22.16 in the book is about natural and synthetic fibers. So nylon is one of the important polyamide fibers made out of amide bonds. And it's certainly super industrially important now. So it's fun reading, but I'm not going to ask you to memorize the stuff that's in there and then put it on my exams. I don't ask you to tell me stuff you memorized on the exams. I ask you to solve problems using your knowledge of organic chemistry. That's why I tell you to practice working problems. And then finally, section 22.17 is biological acylation reactions. I'm not even sure what's in there. I forgot already. A lot of those start with thioester derivatives. And there's also the formation of all the amide bonds in the peptide backbone of every ribosomally synthesized peptide that's produced in the living organisms on the planet Earth. So fun reading. I don't ask you to memorize things and then ask you those questions on my exams, but certainly cool to know why these mechanisms are so important, especially if you're taking biochemistry classes here at UC Irvine or in other places. All right, let's go ahead and talk about another class of functional groups that are related to carboxylic acids, but not exactly carboxylic acids, and that's nitriles. So the 5th edition of the Janus Gorzynski-Smith textbook that we use puts nitriles here in chapter 22, so that they're grouped together with carboxylic acids, and conceptually that makes sense. I think in the 6th edition they might have moved nitriles to a different part of the book. But when I look at a nitrile, it looks kind of like a carbonyl. A carbonyl group has a heteroatom, an electronegative heteroatom bonded to a carbon, multiply bonded to a carbon. I'll just put RO here, but that could also be an amide or a chloride. And so for the same reason that I want to add nucleophiles to carbonyl groups, I also feel like it ought to be easy to add nucleophiles to nitriles and kick the electrons up to the electronegative nitrogen atom. That's why it's grouped together in this chapter, even though it's got a CN triple bond instead of a CO double bond. Okay, what reactions do we know of that involve nitriles, and what new reactions can we talk about? Or reactions that we kind of mentioned a while ago that I said were secret. So we know a way to add cyanide anion to carbonyls. We have to do those under acidic conditions. And I showed you a functional group called a cyanohydrin that you make using hydrocyanic acid. But we don't buy bottles of hydrocyanic acid. You have to make those in the laboratory. You take sodium cyanide powder and you mix it with HCl, both super inexpensive reagents, and that makes hydrocyanic acid, and you have to make these under acidic conditions, or else they're not stable. And once you make a cyanohydrin, in this particular case, the cyanide can add from the top face or the bottom face of the carbonyl. I'll draw one of these three bonds as a wedge. That's kind of arbitrary. I would just need to indicate that you generate two enantiomers. We use this online system, Sapling Learning, for both our homeworks and for our exams, and it doesn't allow you to use this E+ abbreviation for an enantiomer. So if you wanted to indicate the existence of the mirror image molecule, you'd have to draw it for our exams on the Sapling system or on the homeworks. You wouldn't be able to just abbreviate that as E+. That's too bad, because that's a nice little way to save time when you're drawing stuff out. When you, back in chapter 21, when I first introduced this idea of adding HCN across carbonyls, I told you that there was this reaction we could do where we hydrolyze this, and the conditions are harsh. It's the same harsh conditions for hydrolysis of amides. The first thing that happens in a 6-step mechanism is hydrolysis of the nitrile to an amide, and then the amide gets hydrolyzed to a carboxylic acid in another 6-step mechanism. It's a long mechanism, 12 steps, and the conditions are 6 molar hydrochloric acid, just like hydrolysis of amides, water, and 100 degrees. And you need to know that. You need to know those conditions for hydrolysis of nitriles. And in this case, it would give you a mixture, a racemic mixture, you know, just like this is a racemic mixture over here if you start with a racemic mixture. Okay, way back in the chapter on SN2 reactions, you learned that you could do SN2 substitution. Cyanide is such a slender nucleophile. If you're trying to avoid elimination reactions by using really unhindered nucleophiles, cyanide is about as unhindered as it gets. It's like an arrow. Boy, so, and you've got that cyanide there. And of course, benzylic bromide is a great electrophile for SN2 because there's no beta hydrogens. You don't have to worry about competing elimination reactions. This would be a great way to do SN2 without any elimination side reactions. And in fact, none are possible because there's no beta hydrogens there. The product of this reaction would be displacement of the bromide. There's that CN triple bond right there. And of course, just like up above here, if you wanted, you could hydrolyze that nitrile to a carboxylic acid. What do we need? We need 6 molar hydrochloric acid. That's not quite 12 molar. That's as concentrated as aqueous hydrochloric acid gets, but 6 molar is like you just take a bottle of concentrated hydrochloric acid, take some out and dilute it 1-to-1 with water, and it's still pretty concentrated. You need those concentrated conditions for hydrolyzing amides and esters. And you have to boil it to get those to work. But that's how to make it. And once you have a carboxylic acid derivative, you can do all kinds of things with that. You can get amides with DCC or convert it to an acid chloride with thionyl chloride and heat. Again, don't worry about the mechanism for hydrolysis of nitriles. I would love to go into more detail about that, but the mechanism is 12 steps long, and honestly, nobody, I don't think anybody here at UC Irvine on their exams is going to ask you a 12-step mechanism on the exam and then grade all 12 of those steps. So yeah, that's just a little hint. That's all. I don't want to tell you don't learn it, but I don't think anybody's going to ask you that 12-step mechanism. It's very cool. Okay, a CN triple bond. You can add nucleophiles to CN triple bonds a lot like you add nucleophiles to CO double bonds. So one reagent that you can use on nitriles that we also used for reducing esters to aldehydes is DIBAL-H. And we have to follow that up with an aqueous workup. So This doesn't stop at the CN double bond. You might think that it would stop at an imine, but under the hydrolysis workup conditions, the imine intermediate that you generate gets hydrolyzed all the way to an aldehyde, and you simply need to memorize that. Notice there's no CH bond here. That H comes from the an aluminum H bond in the reagent, and again, there's an H here that gets added. We usually don't draw CH bonds, but so if you have a nitrile and you have to say, here's how I'm going to turn that into an aldehyde, DIBAL-H will do that. And once you have an aldehyde, boy, you can do Wittig reactions, add Grignard reagents, make imines. Aldehydes are so reactive. The other thing we can do with lithium aluminum hydride, and I'm just now realizing there's a mistake on this slide. The symbol for aluminum is capital A, lowercase l. Let me just draw it out. That's not uppercase L. So lithium aluminum hydride will add 2 hydridonucleophilic groups to this carbon atom here. And so the product of that reaction is going to be a benzylic amine in this case, right? There's going to be 2 carbon hydrogen bonds there. There they are. We'll talk more about this reaction. I'll remind you of this reaction when we get to the chapter on amines. We're going to have an entire chapter on amines. And I'll remind you of this pattern that, oh, you add cyanide to something, and then you can reduce the carbon of the cyanide into a CH2 group. And it's a kind of an easy way to add a amino-methyl functional group, is this add a cyano group first and then do a lithium aluminum hydride reduction. So you can add other nucleophiles to nitriles. So that's the way the hydrolysis works, is you add water as a nucleophile under acidic conditions. But you can also make carbon-carbon bonds by adding Grignard reagents to nitriles. Let's go ahead and take a look at that. So if we add ethyl magnesium bromide or ethyl magnesium chloride to this nitrile, right, we're going to end up with, after a hydrolytic workup, we're going to end up with a CN double bond. The workup conditions hydrolyze the imine intermediate into, I'll draw this out as ethyl here since I drew it as ethyl there. We'll end up with this carbonyl group, a ketone. So what's happening there? Well, what's happening is this carbon-magnesium bond is super nucleophilic. You already know that it adds to carbonyl groups, so I don't think there will be any surprise to you that this nucleophilic bond should add to this carbon-nitrogen bond, that carbon-nitrogen multiple bond, and forms a new carbon-carbon bond. I'll draw all the lone pairs on the nitrogen, and that's just going to sit there. There would be a bromomagnesium counterion. Right? You need a counter cation here for the N-. That'll just sit there until you work it up. And when you protonate this in the aqueous workup, the imine that you generate, when you protonate that, you'll end up with an NH group, won't be stable. It's going to continue to hydrolyze all the way under the conditions of the workup reaction. So I'm not going to draw all the steps in the hydrolysis of an imine, but ultimately, after this 2-step sequence, you get a carbonyl where you used to have a CN triple bond, and that's how you make carbon-carbon bonds with nitriles. Okay, we're done with chapter 22. It's the chapter on nucleophilic acyl substitution. Over and over and over, I've shown you addition to carbonyls. We substitute groups on carbonyls by adding nucleophiles to the carbonyl and pushing the electrons up to the oxygen. You can see that nitriles follow a similar looking pattern where we add nucleophiles to the CN triple bond and push the electrons up to the nitrogen. And so we've never seen any one-step displacements like SN2 at a carbonyl. There's no such thing as one-step substitution of carbonyl derivatives. It always goes through some kind of a tetrahedral intermediate. When you're talking about esters, amides, acyl chlorides, carboxylic acids, always through some tetrahedral intermediate. Okay, great job on that exam last week using a format, an online format that we've never used before, that sapling system that you've been using for online homeworks here at UCI since the beginning of the year. We're doing remote instruction because of the campus shutdown and coronavirus. So I think a lot of you were worried about the format of the exam, and I want to encourage you to invest in in the format of our last exam, which was also the same format as the practice exam that I made available ahead of time. When I ask you mechanism questions, they will be formatted on our next exam the same way they were formatted on the practice exam, the same way they were formatted on exam 1, where if I ask you to draw arrow pushing, I'll say draw 1 lone pair if you need it, and none if you don't. Not more than 1 lone pair. You have to keep track of formal charges. I'll have questions where you have to draw the product in the box. I'll have questions where you have to draw the starting material in the box. I'll have questions where you have to select a reagent from a reagent menu. That's easier than you thinking up the reagent recipe, those kinds of multiple choice selection. I'll have spectroscopy questions on there, just like the exam 1. So the format of our next exam will be formatted in the same way that we formatted exam 1. So I know that was a little bit unfamiliar and stressful to prepare for a new testing format. You guys did a great job of adapting to that. Keep working problems, work problems on acyl substitution. It's super important. So glad we're finally getting to the carbonyl chemistry that really serves as the meat of organic chemistry, and getting past all of this SN2 business that is not really, that's not the way biology works or synthetic organic chemistry works. Okay, so great job, you guys. Stay connected with other people, stay safe, stay sane, and I will see you on Wednesday.